So I'm going to be talking about the ANEC and things related to the ANEC. The first part is motivation. So I gave a talk about the ANEC and things related to the ANEC at Strings a couple weeks ago.
Yeah, is microphone unmuted?
Yeah. Should I put it higher? How's that? Better? Okay. So for a sort of vague overview and some survey of results and topics, I refer you to the video from the strings talk, the review talk. So I'm going to skip that. Okay, we're done with part one. So the second part of the lecture is to derive the ANEC sum rule. So the goal here is to derive the statement that curly E, which is the ANEC operator.
I don't think your mic is unmuted.
No?
Yeah, there's a mute button on the top. I hope that the speaker's on. Yeah.
Testing.
Okay.
But you can't hear me? Should I shout? Okay. So we want to prove that the average null energy operator is positive. This is integral du from minus infinity to infinity of TUU of u at v equals 0 and x perp equals 0. And the basic thing that we're talking about here is proving this is a positive operator. Although really, it's not just positivity of this operator that we care about. There's a whole set of ideas that connect to the light cone bootstrap and other things that you've learned about. And I'm just going to sort of take this as the guiding idea. That's right. Yeah, I just picked could be anywhere. So the kinematics, which I'm hopefully going to draw once and for all, are as follows. I've picked light cone coordinates. U is t minus y. V is t plus y. This is a picture in Minkowski spacetime. And that's the u that's appearing there. It's a null coordinate. And we're going to study the correlation function g of uv equal to, this isn't going to fit. It's not going to work. G of uv is equal to O at y equals minus 1, psi of uv, psi of minus u minus v, O at y equals plus 1. So the kinematics on this picture, we have an operator O in each Rindler wedge here, one on the right and one on the left. And then we have this operator psi, which will go up here somewhere. So this is psi of uv. And the other one is reflected across the Rindler horizon, psi of minus u minus v. O here does not need to be a primary operator. It can be anything. At some point, I'll set it to be a scalar operator, but mostly it can just be anything. Okay, so I'm going to send this up here, and we'll just keep this picture for reference. I missed. So the basic sketch of the relevant, so what I'm going to do is first sketch the strategy and the relevant ideas, and then I'm going to go back and explain some of the properties of correlation functions that we need. So the basic ingredients here are, first of all, the light cone OPE. So you've already heard about light cone conformal blocks, but for our purposes, it's going to be important to write this in terms of the null energy operator. So the formula, the important formula here is psi of uv, psi of minus u minus v, in the limit v much less than 1 over u, much less than 1, is proportional to 1 plus c psi psi t v u squared times the null energy operator. So the limit that's going to be relevant here is a limit in Minkowski space where we take two operators to be null separated. That's this small v limit. But then we take them to be far apart in the other null direction. Okay, so first we take, so there's an order of limits here. We don't do it simultaneously. We first take them this way, the psi operators, and then we send them out that way. And the statement of the light cone OPE is that in that limit, the leading non-identity contribution is just the integral of TUU over the line connecting them. The limits on the integral go to infinity because of this double limit that we're taking. So that's why the integral is all the way from minus infinity to infinity.
What are the corrections in this formula? Because I always get confused when people talk about double limits. Can't you just say what are?
I'll give an exact formula later. We'll get the exact formula and see how this comes in this limit. So the point here is just that this relates properties of the 4-point function to the NAC. Okay, so now when we plug this into the 4-point function, we have expressions like this. So that's why we're studying the 4-point function in order to understand the NAC. It's because this null energy operator is one of the leading contributions and is the leading contribution in this limit. So by studying properties of this 4-point function, we're going to learn about the null energy operator. The second ingredient is causality. So by causality, I mean causality in the microscopic sense. Which in our case is the statement that psi and psi commute. So we're going to keep them at space-like separation. Causality is the statement that operators commute at space-like separation. Where is that going to come in? It's going to come in by telling us where this it's going to tell us the analyticity properties of this 4-point function. Okay, so commutators in a 4-point function come from discontinuities across cuts. Okay, so the statement of where commutators vanish is precisely a statement about where the function is analytic. Okay, so this is going to tell us where that function is analytic. And once we know where it's analytic, we're going to do what all analytic functions want us to do, which is integrate them on a closed contour and set them equal to 0. And what we're going to find, so what we're going to do is we're going to choose a contour such that this integral, g equals 0, becomes the statement O, E, O is equal to an integral of the double discontinuity, the double commutator that David talked about an hour ago. So this is the d disk of G, and, well, okay, so ingredient 3 is unitarity. I've secretly used unitarity already because this statement about the interplay between causality and analyticity also requires unitarity, so I've secretly used it already. But in the end, in step 3, I'm going to use it again to argue that d disk of G is positive, and that's the derivation of the ANAC. Okay, so that's the strategy, and that's what I described in the talk in Japan, if you watch those lectures. The goal in these lectures here will be to understand the fundamentals behind these 3 steps, to explain the details of these 3 steps, first of all, and second of all, to see how these calculations are related to the propagation of signals in anti de Sitter. Okay, so the connection to ADS is that, well, we'll see what the connection is, but the short story is that these are related to time delays of signals in ADS. So again, on the bulk side, you have a relationship between the ANAC and causality. And then part 3 will be to explain the relationship between what I'm talking about here and the Lorentzian inversion formula. Okay, so you might notice that this looks similar to the inversion formula. Okay, it's some 3-point data on the left is equal to some integral of the double discontinuity. Now, this is not the inversion formula because the inversion formula has this funny, the funny conformal block showing up in this integral. But I'll explain sort of how that fits together and how you can think about the inversion formula in the same way that you can think about the derivation of the ANAC. And I'll give another derivation of the inversion formula that's sort of very hands-on and direct. Okay. Questions so far? Yeah.
O can be any operator, but psi has to be primary operator.
Psi is a scalar, primary. That's right. Yeah. Thank you. Other questions? Okay, so step 1. Step 1 was a light cone OPE. I'm going to sketch both the CFT derivation and the holographic derivation, and the details are in the exercise that everyone's going to do this afternoon. Okay, so we want to understand that formula over there. Psi is 1 plus the null energy. Okay, so the CFT derivation, well, there's lots of ways to derive this in CFT. Actually, I missed David's first lecture. You didn't derive this already, right? But you talked about some shadow technology. Okay, great. So I'm going to do this quickly, assuming you've sort of seen some shadow techniques. The idea is the following. It's a little bit easier to derive this by starting with a time-like configuration. You know, we're ultimately interested in psi and psi being space-like separated, but I'm going to start with them time-like separated, and then I'm going to analytically continue. This is just a little easier to use the shadow formalism when things are time-like separated. So the CFT derivation is as follows. The OPE of psi with psi, we want to look at the contribution of the stress tensor to this OPE. And when things are time-like separated, you can write this as a 3-point function. So this is the psi t OPE coefficient. I'm not going to make t canonically normalized, so we have to divide by, I'm not going to make it unit normalized, so we have to divide by the 2-point function of t. And then we do an integral of psi t shadow times t. The tricky part here is understanding the domain of the integral. So if you were to do this over all of space-time, then you wouldn't have the right singularities in the limit. But by taking these two things to be time-like separated, we can get the right answer by integrating over the diamond, over the Lorentzian diamond between these 2 points. Okay, so having these 2 physical points, you shine the light cones forward on this side, you shine them backward on this side. So this is in d dimensions. So there's some very tilted causal diamond region here. Does this picture make sense? There's this very tilted causal diamond. And if you do the shadow integral over that diamond, that defines the stress tensor appearing in the OPE. So there's 2 things that you have to check to be sure that you got the right answer. One is that it makes sense conformally in terms of conformal invariance, and the other is that it has the right singularity. So in this case, it obviously has the right conformal transformation properties, so we only need to worry about it having the right singularity. And the fact that if you bring these 2 things close to each other, the integral localizes to just points that are very close, ensures that it has the right singularity. So this would not be true like if we just integrated all over all Minkowski spacetime, and that's why there's the right integral to do. But I think that's the best answer I can give.
I guess when we write the T in the Euclidean region, like we understand every single term of the T makes sense because the whole thing is convergent, and then it makes sense to talk about every single term. Here you said, well, let's go to the most complicated region from that point of view.
To me, this is just
expansion, and there's just one term in that expansion.
No.
In which sense is this term more important than infinitely many other terms that are present?
This is the full contribution of the stress tensor. So I haven't talked.
What's the definition of the contribution of the stress tensor?
If you were to plug this into a 3-point function with t, it would give the correct psi t 3-point function. Or if you were to plug it into a higher point, into a 4-point function, it would give the conformal block for stress tensor exchange.
You want to plug it into some other 4-point function, not t.
Right. So if you plug this formula into that 4-point function, it will give you the stress tensor conformal block of this 4-point function. Yeah.
For maybe for a physicist of a certain age, couldn't you also, maybe conceptually, couldn't you also, if you wanted to, derive this from the light cone OPE of Ferraro, Grillo, and Gatto?
Yes.
So that it's just writing that hypergeometric function as an integral of a 3-point function, so checking that you can do that.
That's right. That's right. It's really just, if the way to get an OPE is to write down all the operators there can be, and then make sure you get the right 3-point function. If you've done that, then you've succeeded in doing the OPE. And so this is a trick that does that. I would think of it that way.
That is already present in the structure, right? In the structure of the psi tilde.
Yes.
So why does it depend on your integration region?
Well, you could pick up extra. So, for example, if it's easier for me to say this in terms of the conformal block. If we were to integrate over all of space-time and then plug that into the 4-point function, you wouldn't just get the conformal block, you'd also get the shadow conformal block. Okay, so you get weird extra singularities that you would then have to figure out how to get rid of. If you do the integral this way, then it takes care of that for you. So if you just take this 3-point function and then take the null limit v to 0, then what you find is the 2-point function times u squared v c psi t over ct integral du prime from minus u to u 1 minus u prime squared over u squared squared TUU of u prime. This is an easy calculation. What's happening is this diamond is becoming basically just a line. If you take the null limit of these 2 points to here, the diamond just shrinks to a line, and you do that integral, and this is what you end up with. That prefactor there comes from the geometry of this diamond as it shrinks to a line. If you think about this in terms of operators, then the way to think about it is to expand this out around 0. Okay, so you can take this integral, and you can start doing a Taylor series expansion in T, and then just do the integral. Okay, so if you do that, then obviously you're going to get contributions from TUU of 0, du, TUU of 0, du squared, TUU of 0, and so on. So this is a way, this integral is just a trick for keeping track of all of the operators of this form that appear in the psi OPE. And so it drops all the other operators, but it gets exactly the right OPE coefficients for all of these operators. What's special about these operators is that these are the operators in the OPE of lowest twist. Okay, so as we know from before, when you go and work in the light cone limit, the most important operators are the operators of minimal twist. And for the stress tensor, those are the operators of minimal twist.
Does that work for all the operators appearing in the OP?
Does what work?
Changing this sum to an integral of this kind?
Yeah, the fact that this was the stress tensor was not particularly important. The details of the kernel will change, but it works similarly. Okay, I did that sort of quick because I think people have seen the light cone OPE various ways. There's a much more brute force way of getting this formula, which is just to plug this into the psi t 3-point function and start figuring out the coefficients that all these operators have to have in order to get the right answer. That's the brute force way of doing it. If you do it that way, then you get all these crazy gamma functions and stuff in the intermediate steps, and then you have to resum them and realize that there's an integral. So this is sort of the quick way of doing it.
Were you going to say something about the continuation, or that's fine?
Yeah, you just take v to minus v, and now you have the answer in the space-like case. So it's the same formula in the light cone limit. If you're not in the light cone limit, it's a little more subtle.
That's not the contribution to that stress tensor block, right?
It's what?
That's not the contribution to that stress tensor block. It's only those guys which.
The first line is the contribution of the stress tensor block. The second line will give you exactly the 2f1 light cone block when plugged into a 4-point function.
I thought taking the v going to zero limit only restricts you to also the descendants which have minimal twist.
Yeah, so that's this. It's the operator and the descendants, all of which have the same minimal twist. Okay, so I did that sort of quick, but that's because what I really wanted to do was give the holographic derivation of this formula. And this is sort of what underlies the intuition for the ANAC and what the ANAC has to do with causality and time delays. Yes?
Just a question, is there an easy way to see why we would expect the stress tensor to dominate this next order contribution, like some other operator?
Sorry, say that again. To dominate the what?
You've calculated the contribution of the stress tensor, but you haven't shown this is the dominant contribution. I mean, hypothetically, there could be another operator.
Yeah, so the dominant contributions in general are the lowest twist operators. So the lowest twist operator, the lowest twist spinning operator is always the stress tensor because the conserved operators have minimal twist. So among spinning operators, this is certainly the lowest twist. There's the possibility of scalar operators with lower twist. Those don't contribute to what I'm going to talk about, and we'll see why. It's basically because there's an enhancement that comes from the spin. So if we just want to calculate the correlator and the light cone limit, they're of the same order. We should include them, but I'm going to drop them, and they would drop out of all the final results that I'll talk about.
You're talking about this. Can you also explain why the p is lower than tolerance limit?
Are you talking about the 4-point function or this? So this formula should be taken.
Formula is use stress tensor to form a plot, and everything is fine. But why is it less in this kinematic limit?
You mean in the 4-point function? Yeah. So when we plug that OPE into this 4-point function, we're no longer working with a convergent conformal block expansion like we're happy doing and used to doing in Euclidean signature. And that's because we've done an OPE across a light cone. Okay, so as you can see, we're doing an OPE of these two psis, and that's crossing the light cone of the O's. So we might worry about whether that's a reasonable thing to do. That's what Peter's asking. So there are two ways to answer that question. One is that when we do an expansion in V, the higher twist terms are suppressed in V. So you have an expansion where each term is smaller than the previous term. Usually we're happy enough with that. And what that means is that this is an asymptotic expansion. It's not convergent, but it's perfectly good to use in this regime as long as we're expanding in V and thinking of V as the smallest thing in town. If you're not happy with that answer, then there's a slightly better answer for the stress tensor, which is that you can use light cone bootstrap. Okay, so you take this formula that you have, you take the conformal block expansion that you have in Euclidean signature, you use light cone bootstrap to interpret that in the other channel, and then you use the other channel to go to this Lorentzian kinematics. The other channel is convergent, so everything is perfectly fine if you do things that way, and you'll get the same answer. Okay, so that justifies that this is a correct thing to do, even in the Lorentzian kinematics.
Is the time ordering as you've written there?
Yes.
So that means that psi is hitting the vacuum, right?
No, because psi's not hitting the vacuum. It's hitting O. Okay, so that's why you don't have a convergent OPE. Yeah.
But we definitely want to have an analytic function. If it's just a symplectic expansion, then the second part of the argument is not going to work.
The analyticity will be in U, not in V. So it's an asymptotic expansion in V, and we're going to study analyticity as a function of U. Okay, so I want to derive that same formula holographically. The holographic picture is the following. So here's the boundary CFT. We have our operators psi and psi. And I'm going to assume that delta psi is large. So this is a very massive particle in ADS, not massive enough to back react and make black holes and stuff, but massive enough to travel on a geodesic, so that we can calculate correlators of psi using the WKB approximation. So so this is the radial direction, and we're not in vacuum. We're in some state phi that has a corresponding metric g mu nu phi. Okay, so if we want to calculate the two-point function psi in this state, and we want to do that calculation holographically, then we use WKB, and this is e to the minus delta psi times the length of a geodesic that ends on the boundary at these 2 points. Okay, so that picture is supposed to show a space-like geodesic that goes into the bulk and ends on the insertions of psi. So L gamma is the length of that geodesic, which is equal to infinity. Okay, it's a geodesic that's touching the boundary, so it's infinite. This is not a problem. This is just the fact that there's an infinite renormalization of the operators in comparing bulk results to boundary results. This is something familiar. And the way to deal with it is just to subtract out the vacuum contribution. So instead, I'm going to calculate the ratio of this two-point function to the two-point function in vacuum. Which in WKB is just e to the minus delta psi, L gamma minus L gamma vac. We're going to do this to linearized order in the bulk metric. So to linearized order in the bulk metric, that last formula over there is just 1 minus delta psi, delta L gamma, where delta L means the obvious thing. It's L minus L vac. Yes?
Does it matter what state the bulk is in, as long as it's not the vacuum?
It has to be a geometric state. So I'm putting the bulk in a state that's essentially a linearized gravitational perturbation of the vacuum. It could have other matter inserted somewhere, as long as it doesn't touch that geodesic. So there could be some other operators inserted, like over here somewhere, which have created some junk in the bulk and have perturbed the background geometry. And then we're just measuring, we're using a probe to measure that background geometry. Other questions?
If it's not perturbative, then does it make the calculation faster, or does the formalism does not work?
Well, in principle, the non-perturbative calculation would resum not only the stress tensor contribution. So right now, we're only talking about the stress tensor contribution to the conformal, to the OPE. In principle, if you could do the full non-perturbative calculation, you would get not just the stress tensor, but everything built from the stress tensor, like t squared and t to the 100 and all that stuff. That answer should be, in principle, calculable and universal in holographic CFTs, but will, in general, depend on the theory, because it'll test all of nonlinear gravity. But that gives me a chance to make an important point here, which is that formula that we're trying to derive is not a statement about holographic CFTs. This is a totally general statement about all CFTs. It just came from the OPE. Now we're using holography to derive it, but I'll come back and say a few words in a few minutes about why that's a reasonable thing to do and why we're going to get the general answer. Other questions? So delta L is just the change in the geodesic length between the linearized change in geodesic length connecting these 2 points. Since geodesics are extremal, you can just integrate the metric perturbation over the vacuum geodesic. Right? So the first order change in the geodesic length, we could just use the vacuum geodesic and calculate the change in the length element along that vacuum path. So that makes this calculation very easy to do. It's on the exercises. It takes a couple lines, but I won't go through it, and gives you u over 2, integral from minus u to u, du prime 1 minus u prime squared over u squared, huu of u prime, v equals 0. Experp equals 0. Sorry, I need a z in here. This is the integral of the bulk metric perturbation, and it's integrated over the vacuum geodesic, which from solving the vacuum geodesic equation has a radial profile z gamma of u prime is equal to square root u squared minus u prime squared v over u. Yes.
V is 0, right?
V is HUU is integrated over V equals 0. But what we've done is kept the leading term in V. So we've taken V small, but this is the leading contribution.
So you do this integral with the leading term in V and then set V to 0 at the end, basically?
We're never quite going to set V to 0. When we do these light cone OPEs, we're never setting V to 0. Where did my OPE go? The answer in the end of the day is proportional to V. Okay, so it's always the first order correction in V that we're going to end up calculating. So at this point, what we have is a CFT formula, a bulk formula for this two-point function. But it's a formula that's true in any holographic state. Okay, so if you have a formula that's true in any state, that means you can drop the state and view it as an operator formula. Okay, so that's what I'm now going to do. I'm going to view this calculation of the geodesic not as an expectation value of the geodesic in some state, but as an actual operator. And the dictionary, the usual ADS-CFT dictionary, tells you that the bulk metric operator HUU is dual to the CFT stress tensor with an appropriate rescaling. There's a coefficient here, which is 4 pi g Newton.
See at any point that you're always working in 4 dimensions?
Oh, yeah, I don't know if I said it. I'm working in 4 dimensions. I think I set 4 dimensions right around there somewhere. Oh yeah, right when I went from D to this formula, I set the dimension to 4. So in general, the contribution, the first contribution in the light cone limit would be v to the twist over 2, twist of the stress tensor divided by 2. So in 4 dimensions, the stress tensor has twist 2, so you get v to the 1, but otherwise the formulas are different. The formalism all goes through in any dimension greater than 2, but there's some formulas that change.
You also said that the state that you're working with is a state that creates a small metric perturbation only, right?
That's right.
And here you say that it's valid in any state.
Ah, sorry. Yeah, so I'm going to make that point here. So this is true. This statement about the dictionary is a statement that's true asymptotically close to the boundary. Okay, so in general, if you have some bulk metric perturbation that's deep inside ADS somewhere, you have to use this HKLL formula, which tells you that the dual operator on the boundary is some complicated smeared stress tensor. But as you take the bulk operators and you put them very close to the ADS boundary, then you just get simple relationships like this that just differ by a rescaling. So let's go back to this question of what states we're in. So I misspoke. The calculation that we were doing here is good as long as delta L is small. And there's 2 ways that delta L can be small. It can be small because H is small, or it can be small because V is small. And the important limit here is the important thing here is that V is small. So actually, we're not just working perturbatively in H. It ends up being exactly the same as if you were working perturbatively in H, but up there that should say order V instead of order H. Basically, this is because when you look at this, the ADS metric close to the boundary, the perturbations are just always small because of the Z scaling.
So the metric perturbation depends upon what state you're in, right? The phi, because that's what creates. So how is it completely determined by the T union itself? The T union.
Well, it's an operator. It's an operator. So now we can take the expectation value. This is an operator. Both sides of this are operators. And if we take the expectation value, it's the T in that particular state that corresponds to the metric in that particular state.
Is there a relationship between delta L and delta psi there? Because
Where's delta psi? Oh, this delta psi?
yeah, also in the exponential. I mean, you could.
No, there isn't. That's like WKB. That's just the overall factor of the mass. And then delta L is independent of the mass.
So this is true, for example, in the black hole state.
Yes. So as an operator, the conclusion is that delta L is 2 pi g Newton. I'm just plugging in that formula for z squared along the geodesic. I'm just plugging that in here and calculating, and rewriting this in terms of the stress tensor. So we get 2 pi g Newton VU squared, integral du prime from minus u to u, 1 minus u prime squared over u squared squared, tu u of u prime, which is exactly the light cone OPE formula that we derived up there. All the factors, there's a prefactor here that's important, and the prefactor also works out exactly right. So on the CFT side, the prefactor, you use the word identity to set this prefactor equal to delta psi times some factor of 15 or something, and then if you carefully do all the prefactors over here, everything agrees, the prefactor too. So yeah.
I remember you derived in CFA, it was valid for all data side values. But in the holographic derivation, we take the leading of the term in a large data side, right? So
Yeah.
I really expect to get exactly the same result. I mean, shouldn't we get from like, I don't know, first term in the large data side expression or something like that?
Yeah, this is sort of just a funny thing about scalars, I think, which is that since it's linear in delta psi, you're guaranteed to get the right answer by taking delta psi large. In general, if you wanted to get the right answer at small delta psi, well, you don't have to do it for scalars, but if you wanted to do it totally generally, then you shouldn't be calculating geodesics, you should be calculating Witten diagrams. And if you take the corresponding Witten diagram and reinterpret it as an operator equation, just like we did for the geodesic, then you'll get the answer at any dimension. So the slogan here is that holography near the boundary is basically a trick for doing the light cone OPE. You see the same thing in the light cone bootstrap. So there's a holographic interpretation of all of the light cone bootstrap results. For example, the calculation of anomalous dimensions can be viewed as the gravitational contribution to two-particle states where the two particles are very far apart, sitting near the boundary of ADS. I find a useful way to think about it is sort of that as long as you stay close to the boundary, every theory is sort of holographic. I think this is really just a fancy way of saying that when physics is fixed by the OPE, you can use whatever theory you like to get the right answer, including a holographic theory. But it's often a very efficient way of doing calculations. I won't really talk about the RegA limit in these lectures, but if you want to understand the contribution of operators if you want to understand OPEs in the RegA limit, then you can do something similar. And you can calculate the RegA contribution, say, of the stress tensor or some other operator by calculating geodesic lengths that don't stay close to the boundary, geodesic lengths that probe deep into ADS. Questions? Yeah.
In that limit, then the result that you get from holography CFT won't apply to a general CFT, non-holography CFT. For example, here your result from non-holography CFT match result.
Yeah. Yeah. Well, it depends what you mean exactly. So if you think of this as a trick for calculating conformal blocks in the RegA limit, then it's fixed by conformal invariance, and it'll give you the right answer for the RegA limit of the conformal block in any theory. But it's true that this, in a non-holographic theory, the contribution of the stress tensor that you would get from this calculation is basically unrelated to the behavior of the correlator if the theory is non-holographic. But it will give you the right RegA conformal block.
In this calculation, if I fix, I'm a little bit confused about upgrading the state-dependent statement to an operator statement. If I fix these 2 points, can't I always find a sufficiently high energy state that's non-geometric near the, the area where you care about and you want to compute these geodesics?
Yeah. Sorry. When I say an operator statement, I don't mean. Usually, when people say the words operator statement, they mean something that's always true in all states. I mean operator statement in the same sense that the OPE is an operator statement, which is like true in all states as long as you worry a lot and are very careful about things converging. Okay, so the next thing I'm going to do is I'm going to explain how you derive the ANAC holographically, and then tell you why this isn't good enough to get the full answer. Because at this point, we've basically already derived the ANAC in holographic theories. So that's what I want to explain. Let's think about the time delay through the bulk. So the situation here, I guess I think I've deleted the relevant picture. Let me draw it again. Here's the psi-psi insertions on the boundary. And I'm just drawing a plane, a null plane that heads out into the bulk. Let's think about the case where the state is a shock wave. So in terms of the bulk metric, a shock wave just means that the metric is 1 over z squared minus du dv plus dx perp squared plus dz squared plus delta of u h of x perp du squared. So the metric is just perfect. It's just empty ADS below the shock wave. It's empty ADS above the shock wave, but there's this delta function metric perturbation on the plane that I've drawn here. Similar statements will apply to any state, but here I can draw a better picture. Then the calculation that we just did was the calculation of a space-like geodesic length connecting psi and psi, right? Okay, so there's a space-like geodesic that sort of goes into the bulk. It hits the shock wave, and when it hits the shock wave, it jumps. So there's some delta function that you have to integrate across the shock wave, and if you solve the geodesic equation, you find that it jumps. So it jumps by an amount delta v, and then it comes out the other side and connects to the other psi insertion. The amount that it jumps by, delta v, is z squared h at the crossing point, where the point in the bulk where it crosses that shock wave, which is the same as just z crossing squared integral du HUU. Okay, so this is the calculation that we already did. This is the contribution. This is exactly what showed up in that light cone OPE. Now, for holographic theory, we can now, yeah.
Could you say more about that last equality? What's h in the middle is the h of x per or something?
Here, this is h integrated over the geodesic.
No, in the middle.
In the middle.
At the crossing.
That's this function here. This is just what you get by doing the delta function solution, putting the delta functions into the solution of the geodesic equation.
This is not a case of this particular correlator that you're talking about, right? Because there's some operator in the middle that is inserted.
This would be a very, this actually is the same correlator, but to view it this way, you would have to boost. You'd have to boost the O's, and if you boost those O's by a large amount, then you get exactly this picture. Although for now, I'm not really talking about that 4-point function. We're just talking about general properties of this correlator.
Oh, sorry, what do you mean? I don't quite understand. No, in this case, did you fix the endpoint of the geodesic, or
Yeah.
you fix the endpoint of the geodesic?
Yes.
No, what do you mean by the jump? You mean the jump across the?
I mean, there's still a you still have to solve the geodesic equation, and when you solve the geodesic equation,
What is this? What's the meaning of this derivation?
it's how much, when you solve the geodesic equation, it's how much the geodesic jumps from just above the plane to just below the plane. Maybe you're asking physically what it corresponds to, and that's what I'm about to say. Okay, so at this point, we can immediately see that the annex has to be true in holographic theories. And the argument is the following. It's not, from this picture, it's not obvious. Okay, we have some, we're not sending signals here. We're calculating space-like probes. These things are space-like separated. It's not obvious. I have no immediate intuition for this jump in a space-like geodesic needing to be a positive number. There isn't like a physics experiment where something jumps in this space-like calculation. But the point is, in holographic theory, I have another option. Instead of calculating this space-like probe, I can actually send a signal. Okay, so here we were talking about a space-like correlation, but now let's actually send a signal. So we'll start the signal way down here somewhere, and we'll make it go. I want to hit that same spot. So we'll send a signal on null or slightly time-like trajectory. So it's going up in the u direction, and it hits the shock wave at that same spot. This geodesic obeys exactly the same matching condition across the shock as the one we were just talking about. Okay, so this physical signal will experience a time delay delta v. The physical signal, which you can think of as a null geodesic, has time delay delta v. And if you have a physical signal, if you're sending a physical signal, then it better not have a time advance. It better have a time delay. So this implies the annex in holographic CFTs. But just because we've already shown that g minus 1 is basically the same as this integral of the nec, which is the same as this change in the space-like geodesic length, which is the same as this delta v of the physical signal. Yeah.
You haven't said anything yet about the absence of small twist scalars.
Yeah, so in this case, this 2 here is actually a spin. Okay, so this will be this contribution will be bigger than the contribution of a scalar. Sorry, no, let's see. A scalar will be suppressed in V. Actually, in this argument, I'm not sure what to do about the scalar. When we come to the CFT argument, then we'll be able to get rid of the scalar. I'm not sure what to do in this case.
Haven't you shown ANAC just not in any state, but just in a shockwave state?
No, I did that for the picture, but actually the delta V, the total integrated time delay that you would get in a non-shockwave state is also delta V. Will also give you the NX. By the way, I should have mentioned that I'm not really giving references. This is a calculation of Kelly and Wall, and you can find all the references in the slides from the strings talk.
So, for the scalar contribution, it actually goes down by one more power of G Newton, will it? Rather than the higher twist.
No, I don't think so. I don't think so.
I'm still confused because to have a time delay, you have to have a region which is flat in the past and flat in the future. So I don't see how this type of argument can work in any state. What if you have a state where the metric is curved everywhere?
Agreed. Okay, so by any state, the ANAC, even the whole statement of the ANAC is only a statement about states where the energy dies off far away. If you have states where the energy, like you can have states in Minkowski space with infinite energy, and there's no meaningful notion of ANAC. You need the energy to die off towards infinity, and the same is true here. That when you say any state, you really mean states where this integral makes sense. That'll be the case for any state that you produce by inserting local operators in any bounded region near the origin. But if you start, inserting like an operators that go all the way out toward infinity, then you won't have any meaningful bound anymore. Okay, so in the holographic case, we have these physical signals, sort of pictures that we can draw, so we can understand why these corrections to space-like geodesics are related to physical signal propagation. And then you just immediately can see that these corrections to space-like geodesics have to have a certain sign. But in a CFT, I don't know how to make that argument. I mean, from a non-holographic point of view, I don't know how to make a similarly easy argument where you send a signal in the same and get the same delta V. I don't know how to do that as a CFT argument. So in the general case, we need to work harder to show that these corrections that these sort of corrections that appeared in the correlation function actually have to come with a certain sign. And that's where the NX sum rule comes in. It's a way of turning this intuition about about physical signals into a theorem about conformal correlators.
So even if you do not take small RegA, you can still do the replacement in the signal.
In the holographic case, that's true. Yeah, that's right. Okay, so that brings me to the sum rule. So remember that we're going to get the sum rule by figuring out where g is an analytic function and then doing a contour integral. So where is g analytic? This David talked about in detail, so I'm not going to give the argument, but I'm going to make the statement again in a way that I think is slightly different from the way David said it. In general, if you have a correlation function OW1, OW2, let me call it O1 of W1, O2 of W2, dot, dot, dot. We want to, you can think of these as starting out as points in Minkowski space, which we then want to analytically continue. And then we want to ask, on what domain can we analytically continue that function? And the way to think about that is then to think of these wi's as points in C1, comma d minus 1, meaning that each point wi has a real part and an imaginary part that each live in Minkowski space. If you set the imaginary parts to 0, then that corresponds to the physical space-time. Then G is analytic actually on a bigger domain than what I'll say, but a sufficient criterion for it to be analytic is the domain imaginary part W1 greater than imaginary part W2 dot, 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 where these funny triangles mean is in the future light cone of. What I'm stating here is basically a covariant version of the I epsilon prescription that David was talking about. So if you think about starting with Minkowski coordinates where everything is just inserted at real Minkowski time, then you can get you can analytically continue by adding I epsilons as long as you order the Euclidean times. The covariant version of that statement is that you take the Euclidean piece and then you think about, and then you define things in terms of the light cone of the Euclidean piece. So this is like, since this is ordering of the imaginary parts, it's a little weird because you're talking about light cones, but it's of the Euclidean piece of the coordinate. Okay, I was going to give a proof of that statement, but I think David basically already proved this, so I'm going to skip it, and you can ask me later if you have questions. What I wouldn't. Okay, it depends. You have various choices of what you want to think of as your starting point, your input, and which one's your output. I don't know if I'd say this follows from causality. I'd say it basically is the statement of causality. It's the same. Now, strictly speaking, causality probably should be viewed as a statement about commutators of operators inserted in the physical space-time. Whereas here, I'm using a slightly loose version of causality where I really mean the full analyticity properties of the correlation function, including off into the imaginary direction. But that's what I mean by causality. Okay, so the last thing I want to do today is just play with the example of the two-point function for a minute. So if we have operator O of tx, O of 0, then we know the two-point function, it's minus t squared plus, let me put a vector x, minus t squared plus x squared to the minus delta. And it's obvious where this function is analytic. It's analytic away from the branch point of the logarithm. So this is analytic away from the light cone at t equals x. If we think about that statement in the physical space-time, then, okay, I don't know how well this is going to come. I'm going to try to explain how I like to think about these pictures in Minkowski space-time. We'll see how this goes. But maybe if it doesn't make sense, we can talk about it after. So the way I like to think about it is that you have an operator at 0, and that this operator creates branch cuts on its light cone, branch points rather. Okay, so this operator creates branch points. And the branch cut is the whole future. The branch cut is sort of the whole future here. The light cone is like the branch point, and the future is like the branch cut. So when we talk about time-like separated operators, we're always sitting on a branch cut. It's like, you could tell from here, we're sitting on a branch cut. And we have to decide whether we're sitting just above or just below that branch cut. So the way I like to think about this function is that we should first think about the Euclidean, or the space-like separated correlation function. And then we should think about moving this point around. Okay, so we start with the two this one's not here anymore. We start with the operators space-like separated. And we view this as an analytic function of the coordinates t and x. And now we start moving this we keep this one fixed, and we start moving this point around in the space-time. It's complexified. So if you want to go in the imaginary direction, you can sort of think of that as coming out of the board or going into the board. And as we move it around, we have to keep track of what path we took, because we're talking about a function with branch points. Okay, so when we go up here, if we want to calculate things at time-like separation, then we have to keep track of how we got there. And in particular, we have to keep track of what we did when we got to so there's this sort of plane. You can think of this as like a piece of paper that's being stuck here. Wait, I have a piece of paper. This is going to be even more fun tomorrow when we do when we do the 4-point function. Okay, so like there's this plane here. There's a branch cut produced by the operator at the origin. And we're sending this other operator, and we have two choices. We can land in front, or we can go behind and calculate the 2-point function where it's behind the cut. But when we do that, we have to keep track of sort of where we started. So I sort of think of that as drawing some path that either goes in front or goes behind the branch cut. If you go one way around the branch cut, then you get one ordering of the operator. And if you go, so that corresponds to one of these ways of going around the cut. And the other way of going around the cut gives you the other operator ordering. Which, in this case, we know the analytic structure very clearly because it's just a log, so we can calculate the two paths explicitly. In terms of this, yeah.
What would it mean to go around it multiple times?
In the 2-point function, I'm not aware of any interpretation of that. In the 4-point, the question was, what if you go up here and like go around 5 times and then come back and then whatever? You could just keep going round and round here. In the 2-point function,
Well, is this clear?
what?
Is this clear that you can do it? That definitely does not follow from what, for this function, yes, but for a general key correlation function, I think the analogy breaks down.
Yeah.
That plane that you said is a branch cut. Branch cuts can be moved around, but that plane cannot be moved around. It just sits there, and you can either approach it from one side or the other side, but you cannot like go under the plane in general. Would you agree with that?
You mean go past? You mean like go past it? Yeah, you might.
You cannot analytically continue. You cannot approach this plane from one side and then keep analytically continuing.
Agreed.
Exploring.
Absolutely. Yes. That's why I made it solid. Yeah. And we're going to see the same thing in the 4-point function, is that we always want to avoid trying to go through the plane. And there are physical situations where you do want to go through the plane. So I believe the bulk point, I'd have to think about this. I think the bulk point singularity might be a case like this. There are physically important cases where you have to do that. But we don't really know much about conformal block expansions or convergence properties or positivity properties of the correlators once you do that. Sort of all bets are, like sometimes you can go through, but once you do that, kind of all bets are off about whether the function is analytic or where the domain of analyticity ends and where the singularities might be. Right. So in the 2-point function, you can do it. I don't know of any physical interpretation of the function you get with like a e to the 10 pi I delta, but you can do it. In general, it's not clear that you can even do it.
If you are on the cylinder, you can go to the next counterpart, and then you get these multiple phases.
Yeah, that's right. So right. And that's kind of what happens in the bulk point case, I guess. And that's in the 4-point function. So in the 4-point function, there's a physical interpretation of at least certain multi-windings. I don't know that every multi-winding has a physical interpretation. I guess only some of them do. You know, for example, another thing you could do is you could just talk about the Euclidean configuration. You could just go up and come back down. I don't know of any interpretation of that 2-point function. You could do the same thing in a non-conformal theory, and I don't know that it has any meaning. Okay, I'll just say one more thing. Which is about the commutator. So it's clear from this formula that if you're to calculate the commutator O1, O2, then that's just the plus I epsilon. That was the one where we went on one side of the cardboard, O of 0, minus the minus I epsilon, O of 0, which is the same as I times the imaginary part of just taking one of the orderings. And I'll write a couple more. So that's the same as I sine pi delta times the absolute value formula. And I'm writing these formulas because we're going to see similar things for the 4-point function. We saw some from David already, but we'll see similar things. So like the commutator is discontinuity across the cut, which is equal to the imaginary part of the 2-point function, which is just some phases times absolute value formula. And in particular, another thing you see here is that the absolute value of the commutator is less than any of the, well, let me write it differently. Let me write it this way. Is less than the absolute value of just the ordinary 2-point function. Things are a little different in the higher point functions, but we'll see some very similar looking formulas in that case. Okay, any last questions for today?
It should be 2 sine. Right?
What?
It should be
Yeah.
factor.
Here? Or here? Maybe it was here? Yeah. Yeah. Nope. Okay.
I think the scalar should go down by the weight of the scalar. You took delta psi to be large. Or else nothing stops the scalar from contributing. You can make a composite primary which has the same twist as the stress tensor, but the only reason that the contribution would not dominate is if the scalar itself is heavy. Or else, I don't know how else can you get rid of that.
What is different? It has different kinematic dependence. I mean,
Well, if it has the same twist, then why would it have different?
well, there's twist and spin, and they both enter in here, but